On this positive note, I think it's time to get started. So today we have the pleasure of hosting Eli Waxman from the Weizmann Institute of Science, and he'll be telling us about interesting new mission that's planned for the future about ULTRASAT. So Eli, take it away.
Okay, thank you, Almog, and thanks for the invitation to speak at your seminar. And I'll be telling you about a project that we've been working on for several years now, and it is becoming a reality. So let me share my screen. So do you see the screen?
Yes, we see it very well.
And also the cursor?
Also the cursor.
Okay, very good. So ULTRASAT is a mini satellite that will be carrying a very wide field UV telescope, and which will significantly upgrade our ability to study transient events. The mission is led and managed by a group of us here at Weizmann. So the key participants are listed here. I'm sure you know Avishai Galyam, Eran Ofek, Sagi Benami, and Yossi Schwarzwald. And we have some engineering support. Udi Netzer and Ofer Lapid are leading this part, and our DESI partners in Germany, led by David Berge. The mission is funded by the Israeli Space Agency, Weizmann, DESI, and NASA. And our major industry partners are the Israeli Aerospace Industry, ELOP, and Tower. And I'll explain a bit more about the roles of these different participants later in the talk. Okay, so the main goal of ULTRASAT is to detect and study and alert for transient events. The study of transient phenomena is becoming, I think, one of the major themes of astronomy. The reason is twofold. First, there are many exciting open questions which are related to the sources themselves and to some open physics questions that are related to them, and there are a few examples in this table. So one of our prime targets would be the electromagnetic emission from neutron star merger, neutron star black hole mergers that emit gravitational waves. We want to understand these sources in themselves, but we also want to answer physics questions that are related to these phenomena, the physics of the neutron stars, where did the heavy elements in the universe, from iron all the way to uranium and gold, form. We believe that, as you know, these heavy elements are probably produced by such mergers. Direct measurements of the distances to these events would enable us to measure the current value of the Hubble constant. Another type of event is supernovae. We still don't have a complete understanding of how massive stars explode and how they affect their environments. Another example is the tidal disruption events of stars by supermassive black holes. By measuring these events, we'll be able to constrain the demographics of supermassive black holes at the centers of galaxies and to understand how they affect their environments and so on. So there's a wide range of open questions related to transient astrophysical objects. And the reason that this is becoming, I think, a main theme is that technology now enables us to build very large field of view observatories. So when you study, if you want to study systematically transient events that appear for a short time on the sky, a narrow field telescope is unlikely to enable you to do so because you don't know what to point it to and when. And you need a wide field of view to carry out a systematic study. And this is becoming possible now in a wide range of wavelengths, and optical, like the LSST or Vera Rubin Observatory, in radio, LOFAR and the SKA, in X-rays and gamma rays, both in space and on the ground, like the high-energy gamma ray telescopes, and also in other messengers like gravitational wave and neutrino detectors that have very wide field of view. The ultraviolet is missing from this list, and ULTRASAT is going to change this situation. So there are two key important unique capabilities of ULTRASAT that will enable it to study systematically transient events. One, it has a very large field of view, about 200 square degrees. And the second is that it's going to have very high sensitivity in the UV, between 220 and 280 nanometers. It would reach 22.4 magnitude in 900 second exposure, 5 sigma, about 10⁻³ photons per square centimeter per second. With this very large field of view and UV sensitivity, the volume of the universe that ULTRASAT will be able to monitor is going to be much larger than the capability of any other survey today. So in this graph, you see on the y-axis the instantaneous accessible universe volume, and on the x-axis the wavelength, and it's all normalized to ULTRASAT, which is 10 in these arbitrary units. So you see first that ULTRASAT is going to have a grasp which is some 300 times larger than Galax had. It's going to have a grasp which is a few hundred times larger than any ground-based observatory today. And it's going to have a grasp similar to LSST when it starts operating. And of course, it would have the advantage that it would be observing in ultraviolet, which cannot be observed from the ground. In addition to this huge grasp, the UV has several important advantages. The sky background is low in the UV. The signals from hot sources, these explosive events are very hot at the beginning, so they emit a lot of light in the UV. And this would provide unique information that cannot be obtained from the ground. So we would monitor a volume of the universe, which is several hundred times larger than was possible until now. We'll be doing it at a new wavelength band and with a cadence which is continuous from minutes to months. This is one of the advantages of being in space. And finally, we would have real-time communication, continuous communication with the ground. So we'll have real-time alerts, very fast alerts for any events that we detect. And we will, of course, communicate this information to the entire world community to enable follow-ups with other telescopes. This is a partial list of the science goals of ULTRASAT. And what you have here is some numbers of the events that we expect to detect in a 3-year mission. We will not go through all these numbers, of course. I will talk briefly about 2 of our major science goals, which are gravitational wave sources and supernovae, and even more briefly about planetary science aspects. But I would like to just emphasize here that there would be other types of science that is interesting and ULTRASAT would strongly influence. I would not be talking, for example, about active galactic nuclei. We would have continuous UV light curves for thousands of these objects, and we would be able to do very interesting physics with these observations, study the accretion, do reverberation mapping with short wavelengths, and other interesting topics. So I will not discuss all these things. I'll just give a few examples in this talk. So our one of our key science goals is the mergers of neutron stars. So as you all know, tight neutron star black hole binaries with a separation of few million kilometers will merge by emitting gravitational waves on a sufficiently short time. And this fundamental prediction of GR was finally tested and confirmed by LIGO in 2016 when a merger of a binary 30 solar mass black hole was detected, which led to the Physics Nobel Prize for the leaders of LIGO. And we are interested in events in which one or both of the merging objects is a neutron star. And this is interesting because in such events, part of the neutron star material is going to be heated up and ejected at high speeds. And this highly neutron-rich material, we believe, is one of the favorable possible sources for the R process, heavy R process element production, the rapid neutron capture elements that we see in the solar system. Now, this radioactive material, which is expanding, is heating up due to the radioactive decays, and it emits, therefore, electromagnetic radiation that can be observed. And the detection of this afterglow of radioactive heating is going to be one of the major goals of transient astronomy in the coming decade. The detection of the electromagnetic signal is crucial for doing the interesting physics that we are after. It's crucial for identifying the heavy elements that are being produced in these mergers. It would enable us to study the properties of the neutron star material, which affect the ejected material, its velocity distribution and composition. Accurate localization of the merger is necessary in order to identify the host galaxy, which is necessary in order to measure the redshift and thus obtain a direct measurement of the Hubble constant. And finally, yes?
Ask Ellie, do you prefer us to save our questions to the end, or do you prefer us to interrupt you as you go?
I prefer that you interrupt me as much as you can.
Okay, fantastic, because I also prefer to interrupt if possible. But anyway, one question that I just have is on this R process. What is our current understanding of kind of the integral in terms of the rates of neutron star mergers? Obviously, these are very uncertain right now, but in terms of measuring neutron star element abundances in the galaxy, where are we in terms of, I know that when the first detection of the neutron star collision came out, there was a lot of emphasis on this integral, but has there been a lot of theoretical work subsequent to that, trying to really make clear the kind of decision points in terms of whether or not this is the source of the R process in the future? Or I guess my question is, to what degree is this story basically holding together and buttoned up? And to what degree is there an opportunity in kind of the next few years to hopefully kind of bust this apart theoretically and observationally?
So I think that this is far from being buttoned up as you said. In the single event that we have measured, I think there is large uncertainty about the elements that have been produced. Definitely our process elements have been produced, and we see the radioactive heating of this of the ejecta of this event. So it's certain that these radioactive elements have been produced. However, to what mass number elements were produced there is highly uncertain. And even in the interpretation that the second peak elements have been produced there, so it's above 140, it seems that the fraction of the mass that was, or the fraction of the elements that are composed of these second peak elements is well below the solar abundance. I believe that merger calculations are unlikely to really resolve these questions. I don't believe they are going to be reliable enough to do it. And I believe that by measuring a significant number of these merger events and following them up in the electromagnetic wavebands will enable us to determine which elements are produced at what fractions, and then really answer this question.
And is there work to be done on the other side in terms of really getting that total R process mass solar system down? Like, is that?
I didn't hear this. I just heard the beginning of the question.
Is there work to be also done on the other side in terms of really getting that total mass of the different, the kind of like mass abundance of the different peak R process elements? Like, how certain is that integral number as well? So of course, there's a lot of uncertainties in the neutron star events, right, in themselves and the one that we've seen. But what about what about the sort of integral that we're trying to match up to, like in terms of the integrated mass? Do we have a good handle on that? And I guess I'm just asking this from the perspective of like students and postdocs who may be thinking how solve these problems are. Like they're really not, they're not that buttoned up is my sense. And it seems like that's your feeling as well.
I agree. I mean, even at the fraction of different isotopes or elements produced by our process in the solar system has significant uncertainties, because it does depend on the modeling of the formation of the S process elements. And so I think that there are large uncertainties also on the other side. So there is work to be done there too. Yes. Okay. So let's move on. By probably late 25, with the 05 run of LIGO starting, we expect the horizon of detection of these neutron star merger events to increase to 300 megaparsecs approximately. And with current rate estimates, it should give us some 1 event per month detected. And the expected error box is going to be about 100 square degrees on the sky. This would enable us to carry out a systematic study of these events. The advantages of ULTRASAT in following up the electromagnetic emission are that it can point out almost instantaneously to any point in the sky, any point except for in the direction of the sun. The large field of view of ULTRASAT will cover the GW error box in a single image. And we estimate the sensitivity to be such that it would enable us to detect events out to and beyond 300 megaparsecs. I should also mention that detecting the afterglowing X-rays and radio and other wavebands is very difficult, because bright X-ray emission is only a small fraction of events, and the radio emission is going to be significant over a long time delay, and therefore it would be difficult to follow up, and certainly will not enable us to localize the event fast. I think there was a hand raised. I don't know if there was a question.
I didn't recognize the name, so I removed the user.
Okay, so our timeline is set by the evolution of the gravitational wave detectors, and we need to be in space by 2025. We're ready for the upgraded LIGO observations. The single neutron star merger event that was detected and then for which electromagnetic emission was observed in 2017 was an extremely close, extremely nearby event at 40 megaparsecs. It was a very fortuitous event. It was detected in electromagnetic emission about half a day after the merger. And at the time it was detected, it was very bright in the UV. And this event really provides a strong support for the ULTRASAT GW follow-up for several reasons. First, this event was very bright in the UV, and this was already half a day after the explosion. It probably was even brighter at the beginning. And this implies that we will be able to see these events, if they are similar to 170817, to well beyond 300 megaparsecs. The way by which the electromagnetic emission was detected for this event is that narrow field instruments were directed to the fairly large GW Aero box, and galaxy by galaxy was searched for new sources appearing, and this is how one of these galaxies was detected as the host of the merger. The afterglow was detected. This is going to be very difficult to do for events at 300 megaparsecs, where the Aero box would contain thousands of galaxies. And ULTRASAT would observe the entire field of view in a single image. The X-ray and gamma ray emission from this event would not have been detected had it been at a distance larger than 60 megaparsecs. And the infrared and radio, again, would be very challenging because they become bright enough at relatively late time, the infrared after days and the radio after weeks and longer. So fast identification is not going to be possible using these longer wavelengths. In addition, as I just mentioned before, to answering Jonah's question, so we are certain that heavy elements were produced, radioactive elements, but how heavy is certainly not clear. Is it going all the way to gold or only to germanium? And the early UV measurements on timescales shorter than half a day would provide actually unique information that would enable us to discriminate between different models with different compositions. So all these features are really very strongly supportive of ULTRASAT. Another key science goal is, yeah.
I think Neil Dalal has his hand raised. Is that you, Neil, or is that an intruder?
Both maybe, yeah, sorry. Yeah, so yeah, Ellie, I was just wondering, so you mentioned that the X-ray emission is like much more beamed than this UV emission, is that right? Like, so this is almost isotropic? Like, is that what you're saying?
Well, I'm saying that the bright X-ray emission is very likely beamed. What we've seen in GW 17 is probably not very highly beamed, but it's also very faint. And this is why it would not have been detected beyond 60 megaparsec. If you are lucky and sort of there is a jet that points at you, the X-ray and gamma ray would probably be very quite bright, but this is probably going to be a rare event.
Right, right. But my question was whether or not the galaxy, I mean, are the sources seen by ULTRASAT going to be almost isotropically selected, or instead are they going to be the ones that are pointing at us? No,
so I believe that the UV emission, certainly the UV emission that we've seen from this event is not beamed in any way. And I assume if the other events are similar to this, we'll detect them rather isotropically. Yes.
Oh, wow. That's fantastic. Okay.
Yeah.
So for gamma ray bursts, to be used for measuring H0, there's this problem, right? That the emission is pointed at us, and therefore, like, the distances are somewhat biased. But if these are, well, if these are more isotropic, then that bias shouldn't be present.
Yes, indeed. And okay, so if we are raising these issues, maybe I'll say one more thing. We expect to detect heat of emission, detect the electromagnetic emission without the GW trigger at a rate which is roughly similar to the rate at which we will detect the triggered events. And this is also going to be important. It could enable detection of GW signals that would otherwise not be picked up by LIGO at larger distances, and also at angles which are more difficult to detect by the gravitational waves. So, okay, I think it's going to be very interesting. Okay, the second key science goal is the supernovae explosions. One of the ways to make progress on understanding these, the origin of the explosions and the mechanism is to identify the so-called initial conditions to identify which star exposes which type of supernovae. And so far we have a handful of associations of this type. Essentially, in cases where we were lucky to have a supernova going off in a nearby galaxy that was previously observed with HST and was sufficiently nearby for individual massive stars to be identified, then looking at this galaxy after the explosion, sufficiently long after the explosion, so that the supernova light has declined, you could identify the missing star. But this is a very difficult exercise, and it would not be mapping the full range of explosions. An alternative is to detect the very early UV emission on timescale of less than a day. The emission at this time carries the signature of the progenitor star, its radius, its envelope composition. It also carries the signature of the explosion energy. And so if we measure these events sufficiently early on, we will be able to do this mapping through the UV observations. On the right-hand side, you see some example of serendipitous discoveries of the early UV emission from the explosions of two different types of stars, a large red supergiant and a fairly compact Wolf-Rayet progenitor, probably dominated by helium. And
we have a question from Sarah. Go ahead, Sarah, ask a question.
Hi, thank you. So I was just wondering, with respect to the possibility of observing the kind of early UV emission from supernovae, do you have a sense of, number one, what fraction of nearby supernovae we might have, I don't know, a fighting shot at detecting the early UV emission? And number two, what other sorts of surveys would be able to help improve that fraction?
Yes, so this is, as you said, a really excellent question, because I have this histogram here that shows you the numbers. So what you see here is the number of supernovae that we expect to detect at an age of less than 1 day. So we are going to detect several hundreds of them per year. And the important point to emphasize here is that most of them are going to be red supergiants. And the large number is important for us in order also to map systematically the other types of explosions of blue supergiants and Wolf-Rayet stars. Okay. Now, if you compare it to other surveys like ZTF and LSST, you can see the difference between ULTRASAT and those other surveys. And in the inset, you see the number of events that you will expect to detect at an age of less than 1 hour. And here we still expect to see some tens of events per year, while the other surveys would not pick them up at all. And on the right-hand side, on the lower plot, you see simulated data that we expect to obtain from ULTRASAT. You can compare the cadence and accuracy to the observations that we have today. This would be a major improvement, of course. And by measuring the UV and, let's say, one more color from the ground, we will be able to infer very tight constraints on, for example, on the radius and the explosion energy. Is this okay? This answers your question also, I guess, Sarah? Yeah. Okay. Another science goal, which is of a different type, is issues related to planet habitability. So what does this have to do with ULTRASAT? major efforts are being made to detect habitable planets, mainly around M dwarfs and young solar analogs. And these stars are very active in the UV. And the UV activity of these stars has several implications. One, strong UV activity can extinguish the atmospheres, for example, of planets, and it would certainly limit their habitability. On the other hand, there are some claims that this UV activity is essential in order to enable some prebiotic chemistry. And finally, one of the major biomarkers, which is O3 in the atmospheres, could be produced by UV dissociation of other molecules like H2O and CO2. So you might be deceived to think that you are finding some biomarker while this is due to UV activity. Now, the flaring UV activity of these M dwarfs is far from being well mapped. And the flare rates, especially the bright flare rates, are unknown. And we believe that the UV output is actually dominated by these bright flares. So ULTRASAT will monitor some 10 to the 6 stars, and it would have a very good mapping of the near UV flaring activity. It will enable us to determine whether different types of M dwarfs have different characteristics of UV flaring. I mean, flaring could be related to the rotation or to the spectral subclass and so on. This will enable us to determine which stars are most likely to host habitable planets. And it would enable us also to direct expensive spectroscopic measurements towards the systems which are most likely to host the habitable planets. Okay. So this is just another example. Yes.
Wondering about that connection, because obviously once you start, because of your sensitivity at the early time, you have to have this really fast follow-up on the bigger sources. So are you kind of coordinating with like Las Cumbres or something to actually have a almost, you know, interventionless kind of trigger system? How are you thinking about the spectroscopic follow-up? And also related to that, does ULTRASAT have one filter or several? Do you get a color even from ULTRASAT alone?
ULTRASAT is a single band, 220 to 280, and we are thinking of follow-ups. I have a slide about this a bit later on. So, okay, so we can talk about it in a few minutes, okay? Okay, so let me tell you a little bit about the satellite and the mission. So there we have the telescope, okay, which is going to be constructed by ELOP, which is an Israeli company building space telescope, following the design that we've made at Weizmann. I'll say a few words more about this in a bit. At the center of the telescope, we have the focal plane array. So this is a camera with UV sensitive detectors that I will say a few words about shortly. The camera is the contribution of our DESI, the Deutsche Elektron Synchrotron partners. This is the major experimental particle physics institute in Germany, and they are getting into space with this mission. And the sensors, the UV sensors, are going to be produced by Tower, actually have been produced by Tower Semiconductors, which is also an Israeli company. Now, the telescope is going to be carried by the spacecraft, which is going to be produced by the Israeli aerospace industry. The launch would be provided by NASA, and it is currently planned to happen at the end of 24 or the beginning of 25. We plan for 3.5 years of science mission in terms of reliability. So reliability is guaranteed for 3.5 years, but we will carry fuel for 6 years because the Israeli satellites usually live significantly longer than their guaranteed reliability lifetime. The satellite is mostly propellant, because we were hoping for a direct-to-geo launch, but we will be getting launched to a geotransfer orbit, which is a highly eccentric orbit that reaches the geo orbit only at one edge. And we carry a lot of fuel in order to circularize the orbit. After the circularization, the satellite is going to be about 400 kilograms. The mission profile, we will begin during the first 6 months with an all-sky survey to get a deep all-sky map, which would also serve us as a reference map for transient detection. And it would be 7 times deeper than the Galaxy UV map. Then most of the time we'll be pointing away either in the north or ecliptic pole directions. This is where we have minimal zodiacal light and galactic extinction. And every once in a while, when we receive some alert, which is interesting, like a GW alert, we would point the telescope in that direction. We would reach, as I mentioned, any point in the sky in less than 15 minutes. And most of the sky will probably within 3 minutes or so. And we essentially have an unlimited number of these TOO observation opportunities. All the data will be continuously transmitted to the ground with no delays. A bit about the technology, because this is a real satellite now. So let me show you a bit of this stuff. So this is a blow up of the satellite in its different components, just to impress you that I am doing the job. The telescope. So we set requirements for a very wide field of view and sensitivity. By the way, we could have chosen a different combination of field of view and sensitivity. We could have chosen to have a narrower field of view with higher resolution, which would enable a higher sensitivity and still get the same grasp, the same volume of the survey. But we chose this much wider field of view and relatively shallower depth because we want most of our events to be fairly nearby so that ground-based spectroscopic follow-ups would be possible. So this determines this field of view sensitivity trade-off. So from the optics, we require a very wide field of view. We require a PSF of less than 15 arc seconds. We have a stringent requirement on the out-of-band suppression because the zodiacal light rises very fast in the infrared, and also galaxies have strong optical emission. We require a strong high quantum efficiency in the UV of above 70%, and to minimize background stringent requirements on the dark current and the read noise of the instrument. And finally, there's also a stringent requirement on the buffer. We need to prevent the stray light by a factor of about 10 to the 11 to avoid stray light from the Earth and the Moon. And another function which is a bit unusual is the buffer should also shield the lenses from high energy electrons that would penetrate the lens and emit rank of radiation that would be a very strong UV background for us. So the buffer is a bit heavy in order to absorb these electrons that are trapped in the geomagnetic belt. So some of the challenges in designing the optical system is that we have a limited number of materials that can be used with high transparency in the UV. We are using calcium fluoride and fused silica. The dependence of the refractive index on the wavelength is becoming strong at short wavelengths, and this makes it difficult to have a good PSF across a very wide field of view. Using both calcium fluoride and fused silica, which have different dependencies of this refractive index on wavelength, enables us to compensate and achieve a fairly good PSF. I'll show you in a minute. And finally, we are using a sapphire filter in order to achieve the strong out-of-band suppression. This is the design of the telescope, the Schmidt design. We have a double fused silica calcium fluoride corrector entrance, a spherical mirror, and a double field flutter lens, and then the detector sits here. And we have this huge buffer due to the reasons that I've just mentioned. The entrance diameter is 33 centimeters, the mirror is ½ meter. This is going to be the first corrector lens. The first calcium fluoride blank has already been produced and is now being polished in Winlight to become our first calcium fluoride lens. Okay, some of the challenges, since we have a very wide field of view, we have a very fast system with f of about 1, and the focal depth is very shallow, 20 microns. So this requires high stability, and it requires also a focus mechanism. The telescope is going to be maintained at room temperature, about 300 Kelvin, in order to be able to test the optical system on ground. But the detector is going to be cooled to about minus 70 degrees Celsius. So there are going to be large temperature gradients, which need to be well modeled in order to avoid deviations of this focal plane from the allowed depth. And finally, UV contamination is a very serious issue for the UV, because organic molecules have strong absorption in the UV. So the entire manufacturing, design, testing, and construction of the telescope is going to be carried out in a very high quality, clean rooms, and the materials that we're going to use are going to be materials that do not produce a lot of organic materials in space and so on. Some properties of the camera. This is the focal plane arrays I mentioned. At the top, you see here the UV sensors. The sensor is going to be composed of 4 tiles. These are backside illuminated CMOS detectors with unique high dielectric constant coating. This is essential for obtaining high UV quantum efficiency. You need to avoid accumulation of negative charges near the surface of the detector. One way to do this is by boron, so-called delta doping, which is done by JPL. We are going with a different method, which is this high K dielectric coating of tower, and I'll show you some results momentarily. And there's a special anti-reflection coating to avoid reflection of the UV light. I think I've mentioned the key parameters that are required from the camera, and we are meeting all these requirements with the design that we have. These are real measurements of the quantum efficiency in our waveband. We've tried 3 different types of coatings that were produced by Tower. And on the right-hand side, you see the measurement apparatus at our DAISY collaborator laboratories. And you see that we have several different types of AR coating, all meeting our 70% average requirement. We are going with this T2 option. These are throughput measurements. Okay, again, these are real measurements. This is the out-of-band suppression of several types of filters that we've been considering. And we would be going with this blue VRV filter, which provides us with better than 10⁻⁴ UV sensitivity, out-of-band suppression. So this is the chromatic PSF that we will be achieving with. Now, this is calculated, of course. This is a model, but it's based on the measurements that I've shown you and the optical design. So at our waveband, around 250 nanometers, we would have a PSF, which is around 5 arc seconds in much of the field of view. And the PSF is worse, of course, away from the center and at the center itself. And so it suddenly becomes much worse at longer wavelengths. Okay. But for our band, this is the relevant thing. And okay, so if the PSF meets our requirements, okay, it gets to about 5 in much of the field of view, and less than certainly less than 15, much even less than 12 in most of the field of view. And this is going to be our UV sensitivity, okay, meeting our 22.4 magnitude sensitivity requirement. So much of this curve is now already measured. It's not only a model, and the optics will need to be measured also as well. Okay. Another major component of the mission is the Space Operations Center. All the data is going to be transmitted directly to the ground continuously. So we have a 5 megabit per second downlink from the satellite to an antenna at IAI, where the data will be collected and it would be transmitted to the Operations Center at the Weizmann Institute. The Science Operations Center will be responsible for all the planning of the observations of the satellite, the TOOs, if we decide to go for different modes of survey, this is where the decisions will be made. This is where alerts would be generated and disseminated to the entire community. Data would be archived and analyzed and made accessible to the community, and so on. Follow-ups. You've asked about this, so a few comments about spectroscopic and photometric follow-ups. So we are getting into discussions with partners, but we are also building our own capabilities. So Sagi Ben-Ami, Eran Ofek, and also Avishai Galiam are leading the construction of some follow-up facilities, both photometric and spectroscopic in Israel, and also in collaboration with observatories in Chile. I'll show you in a minute. So the first is our own follow-up instruments in Neutz Madar in the Israeli Negev desert. So there's going to be a photometric large array survey. The idea is to combine a large number of small telescopes to obtain an equivalent large field of view 1.5 meter telescope. It's much cheaper to build this system than to build a wide field single telescope. And this is around Ofek's project. And Sagi is leading a similar effort, combining several small telescopes to do spectroscopy with an effective aperture of 2.5 meters and low and medium spectral resolutions. The construction of these observatories has already begun, and last is supposed to be ready by August next year, and the spectroscopy part a bit later. Okay, so they will be doing other things, searching for other transients before ULTRASAT, but they will be up and running when ULTRASAT is there. In addition, we guaranteed some follow-up time with the NTT and the Magellan telescope in Chile through contributions that mainly Sagi is making to their spectrograph instruments. Okay. So we do plan to have some independent capabilities and some significant collaborations to enable follow-ups in addition to the international community, general community that will be doing follow-ups following our alerts. Now, towards the end, a word about the program structure and status. This is a complicated project. So we have a complicated management tree. No, actually, it's a simple management tree. The construction of the satellite is managed by a program office at Weizmann, which is reporting to an executive board composed of the funding partners. In parallel to this satellite construction effort, we have the Science Operations Center construction activity. We have a science board, which is responsible for coordinating the scientific working groups. I'll say a word about this shortly. And we have an outreach program, an education and outreach program that we are also managing here at Weizmann. There are many decisions taken since the kickoff of the project in September 19. You see a list of significant decisions. The main decision that we had to take last summer was the modification of the satellite due to the modification of the launch that NASA provided from GEO to GTO. This had a major impact on the design of the satellite and also on the timeline and cost. It caused us a 6 months delay in launch, but it almost did not affect our arrival time at the GEO slot, because the direct to GEO launch would not be to our exact slot. We would have to drift in space for several months to reach our slot. And with this GTO launch, we would get directly into our slot. So there's no significant delay in the science operation time. And the total program cost, including launch and science operations, is about $110 million. It's not cheap, but we say it's affordable. We are now at the stage of the critical design reviews. So these are the final reviews, following which no modifications or hardly no modifications will be allowed, and full construction is started. As you've already seen, in order not to delay the project, some elements have already been constructed. The lenses have been ordered, and the sensors of tower have been produced, and so on. So our plan is to have the camera ready within 1 year, telescope within 2 years, full satellite within about 3 years, and then launch at the end of 2024. The risks, the three major risks are the challenging timeline that we have. The timeline is very challenging, and we plan to keep it. So far, we have been able to avoid delays, despite the COVID situation. We have very complex interfaces, which we monitor very carefully. And the contamination issue I've mentioned before, this is something that we monitor very carefully. I've mentioned that we have a detailed outreach and education program. We will not go into details, but we are addressing both high school students and the general public. We have institutes at Weizmann who are expert in these type of activities, and we are collaborating with them on the outreach program. And before the end, I'll say a word about the scientific collaboration. So as I mentioned, there are now 12 science working groups of ULTRASAT working on the different science topics that some of which you've seen on the table. They are open to all the Israeli astronomers and have already been joined by almost all the Israeli astronomers. The NASA return to their investment is 8 USPI slots that would be funded by NASA and would join the ULTRASAT working groups. The project scientist for NASA is James Rhodes, and a call for participating in the ULTRASAT mission should soon be out by NASA. Our DAISY partners received 3 DAISY PIs in the ULTRASAT working groups for their contribution. And finally, we are in advanced negotiations, meaning we've really concluded these negotiations, and we will sign an agreement also with the Rubin, the LSST observatory. We will have joint Rubin and ULTRASAT alerts. We'll have some coordinated observations, and there will be several additional USPIs that would join the ULTRASAT working groups through this collaboration, and Israeli astronomers that would obtain direct access to the Rubin data in return for this collaboration with ULTRASAT. So our sort of science collaboration is strong, and the working groups are working, and I think we are in a pretty good shape for this stage of the project. So to summarize, I believe that ULTRASAT will have a very strong science impact. Our discovery volume, the volume of the universe that we will be observing, is 300 times larger than that of galaxies and 100 times larger than any existing transient survey. So this is going to be a significant, major improvement in our capabilities to study transient objects. It would have a continuous cadence from minutes to months with a very good UV sensitivity at 22.4 magnitudes, and would have real-time alerts distributed to the entire community to enable space and ground-based follow-ups. I believe that this will have a broad impact on a wide range of topics in astrophysics. We've mentioned gravitational wave sources, supernovae. We've mentioned variable and flare stars. We did not have time to talk about AGNs and TDEs and cataclysmic variables and so on, but there will be significant impact on all these subjects. And finally, we'll be doing all this in a relatively affordable cost. So $100 million, including launch and science operation and everything, is not expensive for a significant space mission. Okay. Okay, that's it for now.
So thank you so much. Let's thank Eli again.